All right, now let's continue with this discussion of the underpinnings of this type of big data science. So this is just a reminder of what we already discussed. It has some additional information, like 3,600 people are in CMS, and they come from 183 different organizations and from 38 countries. So this clearly demonstrates the need for the work collaboratively in the slogan for this course. And this also points out what I already mentioned. It cost $500 million just to build each of those experiments. Atlas is essentially the same size as it says here, only 3,000. I'm not certain how accurate these numbers are. Here are the actual 7 different experiments we saw on the picture earlier: Atlas, Alice, CMS, LHCb. The other ones we did not see. There are smaller experiments. Notice this is a European Union experiment, but it has a collaboration with the United States and probably other countries as well. But the fundamental management and funding that went into this came from the European Union. Of course, the US had a machine of this class, the so-called SSC. It was in Dallas, Texas, and that was closed down in some political/scientific events where at some critical time the support of the field or the support of scientists broadly was not enough to preserve the SSC. So actually they were gone quite a long way in constructing it before it was just terminated. And then CERN, the European Union has one feature that's interesting. Once you get something started, it's not so easy to turn it off because all the countries are collaborating. And if one country decides to pull out, the other countries can stop that happening because they'll have various other implications for the whole European Union. So the EU process puts on some stability into projects in Europe. So here are the budgets of which are. If you go to the Department of Energy, I mean, there's some National Science Foundation funding going into LHC, but most of it comes from DOE. DOE also does a lot of other things with experiments and theory of particle physics, and that's almost 800 million a year. I do not know how much the LHC is there, but it will be a non-trivial amount. And if you just look at what it takes to fund all these people, 6,000 people, that's where I sort of estimated $500 million a year across all the countries. Here's a striking feature of this field, and that's the papers. If you look at this, I pointed out there are 3,000 people on these experiments. So here are the beginning of the 3,000 people. We have AAD as the first person, and on this particular slide we get to BAU. So we only got partially through the B's. This page is mainly A's, so it's not surprising when we get through the Z's to the participants beginning with Z, which presumably largely come from China. We have many pages of this particular publication correspond to the people, probably more pages in the people than there are in the physics. And that is, as I mentioned, one of the reasons I gave up was when I did experiments in this field, there were 30 people on an experiment. Now we have 3,000 or 3,500. I also found, being a not terribly relaxed person, that I found working with those 30 people, they were all very talented and committed. Working with 30 people is not trivial. At least in the days when I did it, it wasn't trivial. Nowadays, there are better tools and it's better understood. But the concept, then I could already see that the experiments were getting larger in size, and so I was a little worried and switched to the smaller size collaborations and quicker moving fields that happened in computing research. Here is the sort of this is again comes from my past. This is not from my past, but it's the type of things I used to do. This gives us a picture, a so-called Feynman diagram, telling you what happens when a proton and an antiproton collide. Gluons are produced. Gluons are the particles that bind the quarks together to inside these protons and antiprotons. They have a so-called virtual interaction, which with a heavy particle, the heavy particle couples to this Higgs boson, which is then produced. The Higgs boson cannot survive forever; it always decays, and the decay is. There are actually several final states it decays to. We saw the data from the two-photon decay. This is a gamma zero as a photon. Another possible decay is to lots of leptons. These are electrons and muons and taus, the lepton family. And these are the diagrams which you estimate when you want to try to understand what the Higgs might look like and design the apparatus and to look and see what's the most plausible things to do. As you would study these so-called Feynman diagrams, you would estimate their size, which might be a little unreliable. But something is probably reasonably reliable is what the final states will look like. The constraints of spins and symmetries will tell you what these two photons, the distribution in angular distribution, the momentum distribution for a given Higgs mass. You would be able to estimate that pretty reliably for these types of decays. And that's actually the type of thing I used to do. I used to do phenomenology, which is building models. I should point out that physics, although there's a fundamental theory, that theory is impossible to calculate what happens when the proton and antiproton collide at very high energy. You have some good idea of roughly what's going to happen, but in detail you have no idea, and you have to build models, and that's building models of what happens when this type of thing, when these types of collisions are made, is the type of thing I used to do as my physics research in those days many years ago. And I say that's still the same, much more sophisticated versions of what I used to do. And now at the heart of the so-called Monte Carlo analysis and the planning of these experiments, you notice how big those apparatus were. One feature of them being big is they're very complicated and you're not quite certain how they behave. And the way you understand how they behave is you make a model for the you not only make a model for how the Higgs boson is produced, you make a model for the apparatus, and you produce so-called Monte Carlo events, which you run through exactly the same software that you use to analyze the real events. So that's a huge positive. If you take events which have Higgs particles in them, and you generate them by the Monte Carlo, and then you run them through the science and the actual same software you use to run real events, you can convince yourself you would have seen it, and also you estimate the so-called efficiency, the probability, if you observe a certain number of Higgs boson events, the probability that what fraction of the actual Higgs boson events you saw. So that's how these innocent-looking pretty pictures are used. And now we go on for the rest of this unit into a discussion of some pictures illustrating big science. And then we finally get back into the next unit. We will actually go into the actual statistical analysis of what's going on. Thank you very much. This is Jeffrey Fox finishing this second lesson of the first unit on physics informatics and the discovery of the Higgs boson. Thank you very much.